Hey, good afternoon, everybody. Welcome to the second session of the Thursday Talks of this year. Today, we will be covering the topic of CO2 recovery and valorization. And this session is powered by the FUELPHORIA project, but we will also have other 3 projects being covered in today's session. So before we go into the topic itself, I want to give a brief introduction on the platforms that power the Thursday Talks. So the first one is the Resource.bio. So Resource is established as a multidisciplinary community platform around bioresource recovery. It is a local platform in Ghent, which covers 40 research groups from 5 Ghent faculties and 2 associated university colleges, which are Ghent and Artevelde Hogeschool. We also have the Biorefine Cluster Europe as a co-organizer of the Thursday Talks. So Biorefine Cluster Europe is a European project platform, which was created because we noticed that there was several projects that were dealing with similar topics and they weren't really conversing with each other. Not only that, European projects have a lifespan, and usually when they are over, their project website goes out of functioning after some months or a couple of years, and unfortunately, everything that the project generated gets lost. So with the cluster, we have these 2 main goals of putting together the projects that work on similar topics so they can improve their impact and reach more relevant stakeholders together, and also make sure that their deliverables and outputs stay available after the project ends. So the membership to this platform is free of charge and open access to any European project within the topic of the platform, but it's commitment-based. So of course, the projects that are part of it are expected to contribute to the different initiatives, including the Thursday Talks. So the initiatives are the bulletin and the social media. So the Biorefine has a bi-monthly bulletin where they highlight all the achievements of the projects that are part of the platform. And it's also very active in LinkedIn and other social media with news of events, outputs, deliverables, publications, vacancies. So really increasing the outreach of your project. Both platforms are organized around 6 working groups, which are thematic working groups around the topics of nutrient recycling and management, water recovery, waste to energy, value chain assessment, biochemicals extraction, and bio-based materials and design. So we joined forces to create the Thursday Talks, which happen once a month in the last Thursday of the month from January to June. It's 1 topic per session, and this topic is illustrated with European projects. And this year we are usually highlighting 1 initiative, and then we build a session around it with other projects that interact with the topic, so we can foster collaboration. And the next session will be on alternative proteins on March 26th, also at 2. And you can find more information in the Biorefine Cluster website. The link is here. I'll share this presentation afterwards. Maybe important to also introduce myself. I'm Marcela Souza. I'm the coordinator of the Resource platform, and I also work together with the Biorefine Cluster Europe. And we put together these Thursday Talks to highlight more the advances of both platforms. So today what we have in store for us is 2 mini sessions within our biggest CO2 recovery and valorization session. So we will start by highlighting the efforts of FUELPHORIA and CIRCE projects on CO2 valorization from the food industry. We'll then have a small break, and we will come back with the AgriCO2, FUELPHORIA and SEMPRE-BIO, highlighting their research and activities on CO2 recovery and valorization from biogas. Just a little guidelines on how today is going to run. So I do ask everybody to keep their video and microphone off muted, except the speaker, of course. This is not to overload our connection. If you have a question, please ask it in the chat, and I will read it after the presentation. The speakers will answer a few of the questions directly here, and then if some are unanswered, they can also interact with the participants in the chat. So I do ask you to ask questions. It's supposed to be an interactive session. so far away, and we can have some exchange. And I also would like to inform you that this session is being recorded. So with that, my part is done. And I would like to already invite our first speaker of today from the FUELPHORIA project, Sergio Iglesias Vazquez.
Hello, welcome everybody. Thank you, Marcela. I will share my presentation. Okay, can you see it well?
Yes.
Okay. So, welcome everybody. I'm Sergio Iglesias and I work in CIRCE Technological Center located in Zaragoza, Aragon. And I will present the work done within the European FUELPHORIA project about the production of methane from biogenic CO2 in a wine factory. So, the project is located in Viñas del Vero, Spain. It is a wine factory with more of 1,000 hectares of grape crops. The project will target methane production, and the CO2 will be taken from the fermentation process of the wine procedure. And hydrogen is currently produced by an on-site electrolyzer, and the initial technology readiness level is 5 with a scope final of 7. The aim is to utilize the captured CO2 from the wine fermentation combined with green hydrogen, as I said, as feedstock for a methanation process. This is achieved using novel nickel-based catalyst, and the CO2 will be separated, purified from the fermentation gas, and then stored for the later use, where it will be converted into the final methane. The CO2 generated during the wine fermentation is carbon neutral, matching the amount absorbed by the vines through the photosynthesis. So here are the project partners. Viñas del Vero is the host site, the provider of the CO2 and the hydrogen feedstock. CIRCE, where I work, is the responsible for methanation process development and integration. And University Rovira y Virgili from Tarragona, Spain, does the development of catalysts and methanation reactor. And the demo targets are hydrogen production of 500 liters per hour, a methane production of 2.2 kilograms per day, and a CO2 utilization of a 0.4% of the winery's annual emissions. So in this slide, I show the CO2 capture, purification, and storage system installed at the winery factory at Viñas del Vero. This unit collects the CO2 from the fermentation tanks, compresses it, and purifies it through several filters to remove impurities and some kind of humidity it can have. And the purified gas is then stored in a 500-liter CO2 tank at 20 bars, ready for use or transport to the methanation unit. Then this captured CO2 in this harvesting period that went from the 20th of August to the 9th of September of 2025 has been 17 tons. And from this, only 8 kilograms are going to be used for potassium methanation. It is the capacity of the tank. And the CO2 has a purity of 99-95% with CO, hydrocarbons, ethanol, and water as the main impurities, but they are at a very low level, and sulfur is below the food grade level, so there is no risk for the catalyst. So, okay, sorry. Before testing the catalyst in the demonstration reactor, and while the unit was still under construction, we carried out a full series of laboratory scale experiments at the university. These tests allow us to compare several catalyst formulation under controlled conditions and also to identify the one offering the best stability, activity, and also the resistance to the activation. So we synthesize a nickel-based catalyst as well as several promoted versions of it, adding 3 different promoters to improve resistance to sintering and coking. And all tests were performed at atmospheric pressure with a hydrogen CO2 ratio of 4, which is a stoichiometric value, and a space velocity of 0.54 mole of CO2 per gram of catalyst per hour. And these conditions are representative of the expected operation at the demo unit at Viñas del Vero. Among the promoted catalysts, the nickel prom 3, which is in red in the screen, provided the best CO2 conversion in all temperatures, approaching to equilibrium at 500 degrees and also higher temperatures. And the nickel promoted one sample matched the other one at higher temperatures, but with no significant advantage. So when the best candidate catalyst was identified as the nickel promote 3, long-term tests using real CO2 from the winery fermentation process were done. And the test was performed at 300 degrees, atmospheric pressure, and a hydrogen CO2 ratio of 4 over 1,000 hours of continuous operation, which it's equivalent to 41 days, more or less. The initial conversion was around 85%, stabilizing at 80 after the first 250 hours, with a very high methane selectivity. What's also interesting is that when the CO2 source was shifted from white wine to red wine fermentation, the catalyst behaved identically, showing very robust behavior to the feedstock variations. And this confirmed that the catalyst as the final candidate for the methanation reactor. The co-precipitation method used in the lab produces a very fine powder, which is below 1 millimeter, and is not suitable for a fixed bed reactor, which is the one we are utilizing at Viñas del Vero. So two routes to adapt the catalyst for the demo unit were investigated. The first one was impregnation of nickel and promoters onto a commercial alumina particles. And the second, cold pressing of the precursor powder to obtain larger cylindrical pellets. So here I show you the result for the impregnated catalyst, which is the first method we used. And two samples were prepared, one standard nickel-based formulation and one with a promoter. And the impregnated pellets were large, about 1 octave inch. And as expected, some diffusion limitations affected the CO2 conversions. And the promoted version was a bit more active, but showed some deactivation above 500 degrees. So although the method indeed works, it was not the optimal solution for the demo reactor. But finally, the cold press pellets of the nickel prom 3 catalyst were tested, and these were 3 millimeters per 2.5 millimeter cylinders with good mechanical strength after recalcination. And we operate at 360 degrees and a lower space velocity, closer to conditions expected in the demo reactor. And the catalyst achieved an 82% conversion, remaining stable after 90 hours of continuous operation. And the methane selectivity was very high, with almost no CO or ethane formation, and confirming that this pelletized version was suitable for the methanation reactor. So this is the reactor that we are using for the methanation activities located in Viñas del Vero. The methanation unit is designed at a furnace with two tubular reactors in series, each coupled to a condensate separator to eliminate the water originated in the reactor. And during this first startup, we carried out the catalyst activation procedure and ensured that the system reached a stable temperature region. And at the same time, we perform leak checks across the entire installation to verify full integrity under the pressure we operate in. And we also perform already some catalytic tests that I will show you the results in the next slides. And also we collected the first data using the CO2, the real CO2 from the winery. So here's an overview of the whole pilot plant, where you can see here the reactors into the same oven, as well as the two condensers, which are located here. That separates the water which is producing the Sabatier reaction. And in this final slide, I will show you some first results we have obtained using the conditions you see in the screen. In the first reactor, the gas already contains less than 10% of CO2, and the methane concentration is already quite high, with a conversion above 70%. However, in the second reactor, the conversion barely continues and the methane just yields a bit. The temperature profile confirms what we expect for an exothermic reaction as Sabatier. In the reaction 1, there is a clear hot spot near the inlet that drops quick along the bed, while the reactor 2 shows a much more uniform lower temperature profile. Overall, we prove a stable operation over the full 30 hours we test, with consistent conversion and clear improvement in methane composition across the two reactor setup. I have to correct myself because I said we had a conversion of 70 and it was almost 90. And finally, I will talk about the key aspects in the outlook. The winery sector can serve as a provider of biogenic CO2 for fuel production. And the CO2 from one fermentation, it's a feedstock for renewable fuel synthesis, such as synthetic methane, with minimal treatments prior conversion. The demo aims to perform long-term lifetime tests of the catalyst under industrial conditions, and the system will operate with a stoichiometric CO2 and hydrogen feed of 4, maintaining temperatures below 500 degrees, or trying to maintain this, and working pressure between 5 and 10 bars. We have to improve the conversion in reactor 2 by increasing a bit the temperature while trying to keep the reactor 1 inlet hotspot under control. And we also have to validate the numerical reactor model by comparing predicted and measured temperatures and composition profiles in the upcoming test. And these numerical simulations and the next optimizations will identify the best configurations for technical and economical feasible deployment. So this is my contact, and thank you very much for your attention. Do you have any questions?
Yeah, thank you, Sergio. There are already questions in the chat, and
Okay.
I also have some. Yeah, Thibaut is asking, how is the high temperature for the methanation obtained? Is it a consequence of the fermentation reactor, so a heat transfer exchange, or is there a separate heat source provided, so energy use?
How is the high temperature? I mean, we have a electric furnace, and we heat it with that furnace. And the both two reactors, they are in the same furnace, so we have this PLC control, and we have a set point, and we choose the temperature there, and it's heated electrically. I'm not sure if that was a question.
Yeah, if there is energy input, so there is energy input in your process.
Yeah, there is.
Okay, and Bohan is asking, what's the difference between biogenic CO2 and a commercial CO2 as the feeding? What's the challenge for the reactor with real winery CO2?
Well, let's say that doing it like that with biogenic CO2, we close the carbon loop in the wine factory, because this CO2 that is produced in the fermentation, otherwise it was sent to Ghent. So now we are utilizing this biogenic CO2 for methane. And this methane can be burned in the plant to obtain energy, or also try to condensate it and use it as a fuel for vehicles. And the challenge for the reactor, let's say the CO2 is not really the problem, let's say, because it's already purified, so it's almost 100% CO2. But I would say the main challenges we are having right now is trying to avoid this big hotspot on the inlet of the reaction. The reactor, sorry, at the first reactor, because it can deactivate the catalyst, and we believe the reaction is going too fast. So the second reactor almost do nothing. So yeah, that's the main challenge, I would say. We will try to play with this temperature profile and try to optimize the configuration of the both reactors.
Okay. I have questions, but yeah, if anybody else has questions, please put it in the chat, and I'll switch from mine to yours, your priority. But I have, on the thing. Okay, there is already a question.
Okay.
So Yasin is asking, what methods do you use for the separation of CO2 from the other gases?
Okay.
I guess the pretreatment.
Yeah, as far as I know, because I was not involved in the CO2 capture unit, but as far as I know, there is an active carbon and zeolites, and I think there are two stages of that, and then it directly compresses to the tank.
Okay, yeah, so quite easily. So I had a question on, similar to what was asked between the difference between commercial CO2 and winery CO2, but I was wondering how transferable your technology is to other CO2 sources. I guess quite a lot, right? If you would be able to install this in a cement factory, for instance, that is one of the biggest emitters of CO2.
Yeah, exactly. I mean, as long as the CO2 is purified, so it doesn't poison the catalyst, there is no problem to use biogenic CO2 or CO2 from other source. I don't think so, but at least we need a certain level of purity.
Okay, so maybe there would be the challenge. Maybe these other sources have more impurities.
Exactly.
That require more purification.
Especially, it's important to try to avoid sulfur because it's really poisonous for a catalyst.
Okay, interesting. And maybe building up also on Thibaut's question about energy. So you said that the methane would be used more for energy applications, so either being burned or maybe for fuel a car.
Yeah.
Did you look at the energy balance of your process? Are you generating more energy with the methane than you are inputting in the system, or you still didn't check this?
No, we didn't check it. We are currently performing the life cycle assessment, but we don't know it yet, to be honest. But I mean, the methane reactor is very small compared to the CO2 storage and purification system. So I mean, I'm not sure it's so representative so far. But anyway, we are performing the LCA analysis, but we are not sure yet.
Okay, but anyway, methane is a nice building block for the chemistry industry as well. So maybe even if the energy balance is not good, it's still valuable input. Yeah. And I had, speaking on the size, you just said that it's small, the reactor. I was wondering if you did any calculations of, how big your system would need to be to recover, for instance, convert all the CO2 in a medium-sized winery. Do you have any idea? Is it a big system or is quite a compact system?
I mean, you mean the size of the reactor or how we calculate the
Yeah.
Okay.
No, really the size.
Yeah, I mean, the reactors are 1 meter long, and I know our colleagues from the University of Rovira i Virgili did the calculations for the conditions of the reactor, but we were limited because the electrolyzer had this capacity of 500 liters per day, I think. So it's not really much. So we tried to build the reactor within those parameters. We were a bit limited by the electrolyzer because we also had to put 4 times more in volume of hydrogen per methane. So it's not that was the, let's say, the bottleneck of the size of the reactor.
Okay, so right now that reactor that you showed doesn't convert all the CO2. There's more CO2 being produced. It's just proof of concept.
Yeah, exactly. It's very far to convert it all.
Okay, great. I don't see any more questions in the chat for the moment, but if anybody else thinks of something, feel free to put it in the chat, and then Sergio, I invite you to answer if they pop up. But thank you so much for the presentation. Very interesting.
Thank you.
And let's see, now we'll continue our program with the CIRCE project, which is represented by Carolina Colvée today.
Yes, thank you. Let me see, one moment. Okay, do you see my screen?
Yes.
Perfect. Okay, my name is Carolina Colvée, and I work in AINIA. It's a research center based in Valencia. And I'm going to talk about biorefineries and the CIRCE project, which is an innovative European project and I'm going to talk about the pathway of the microbial elongation of CO2 from beer production into volatile fatty acids mixture enriched in caproic acids. First of all, I'm going, it's not moving now. Now, sorry. First of all, the biorefineries concept, the general concept are those processes that convert residues or waste into high value added products. And as we can see in the picture, there are a lot of kind of substrates that we can use in this kind of biorefineries processes in order to obtain fuels, chemical products, or biomaterials that have a high commercial value. From a problem that is a waste, we can obtain a solution and even a good quality product. Considering the gas fermentation processes, gas such as methane and CO2 can be an important source, an important carbon source for fermentation processes, because CO2 is a sustainable, accessible, and transportable economical carbon source, and as well is interesting because it's compatible with anaerobic digestive systems that, as you know, they are quite common nowadays, and they are really used for waste treatment. With this process, we are able to obtain feeding ingredients, bioplastic, cosmetic ingredients, and other building blocks. Well, here is a picture of my team that we have participated in this project, and here in AINIA, we can obtain different products such as methane, polydioxyalkanoates for bioplastic, proteins, other chemicals, basing our strategies in different electron donors, such as the use of hydrogen, ethanol, or sugars, for example. But now going in depth in the CIRCE project, which is a clear example of an integral biorefinery, we are going to explain the specifically use of CO2 for ethanol production, for caproic acid production. This project, as I said, is an European project, and it consists on 12 partners, which are present in 5 different countries. And the project is going to finish soon. We wish it's going to finish in this summer. So the project, this is the general overview, is based on 2 new bio-based platforms, the insect and the microbial platform. And the idea is to valorize all the byproducts or the wastes that we can obtain from a brewery. In this case, it's Mau San Miguel breweries, that it's in Madrid, in Spain. And the idea is from the CO2, do several processes that I'm going to explain in depth in order to obtain a volatile fatty acids mixture rich in caproic acid. This is useful for feeding industry. As well, there are other processes that from methane we can obtain ectoine, single-cell protein, chlorine-based disinfectants, and in the insect platform we obtain protein-enriched drinks with that insect protein. Here is the specific process that I said I'm going to explain. As you can see, from the brewery, we obtain wastewater, biogas, CO2 emissions from the fermentation processes of the brewery, and ethanol. The first stage, it is the anaerobic digestion, the acidogenesis. In the anaerobic digestion, if you control the parameters, you can obtain the acidogenesis and enhance the volatile fatty acids production. Then with that effluent from this stage, we go to the microbial chain elongation process, in which we include the CO2 emission and the ethanol in order to elongate the carbon chain of those fatty acids. In that way, we obtain longer chains, which has a higher value in the market, and they have benefits such as good digestibility and antimicrobial properties for animal feeding. So the main goal of this part of the project is to generate an enriched mixture of these volatile fatty acids by optimizing the process and by converting that CO2. So Here is the main explanation of what the volatile fatty acids elongation is. This process consists on the reverse beta oxidation pathway. So we are able to elongate those chains by adding carbons into the volatile fatty acid chain. The Clostridium cluveri is a microorganism that is key in the process. It requires CO2 in order to create those additional carbons in the chains, so for anabolic reactions. The use of ethanol is key because it enables us to elongate ethanol itself into medium chain fatty acids or the volatile fatty acids into other ones, such as caproic acid, which is the key in this project. So how did we do it? How did we enhance this production and the CO2 conversion? Well, first of all, we started assessing the acidogenic step. So we introduced into our anaerobic digestion, first of all, a municipal solid waste that we know that it's rich in sugars and other components that are good for the acidogenesis step, so for the volatile fatty acid production. Once we had the desired population, microbial population, we progressively exchange the municipal solid waste for bagasse or spent grain. And as well, we change the regular water for wastewater, so from the brewery. So once we stabilize the process with our substrates, the ones obtained from the brewery, we use the effluent and we put it into the CO2 elongation reactor. Here we introduce the CO2 in order to be bioconverted and to elongate the chains. So in this process, we evaluated several parameters. First of all, in the anaerobic digestion, we evaluated the pH, the hydraulic retention time, that is the time the substrate is inside the reactor, the organic load, the temperature, and in the elongation process, we evaluated the same parameters and the CO2 inlet. Finally, in order to know the yields of our process and the CO2 bioconversion yields, we used our gas chromatography equipment in order to know how is the process going. So these are the main results of the laboratory scale processes we have done. We know that a pH between 5.3 and 5.5 is key in the acidogenesis step for bagasse fermentation. And we saw that by increasing the hydraulic retention time, we acquired a higher concentration of caproic acid. However, as it was the first stage, we wanted to achieve more general volatile fatty acids for elongating it later in the next step. So we chose 6 days as the perfect hydraulic retention time. Then in the elongation process, we saw that a higher pH was great for the process for achieving close to 30 grams liter of volatile fatty acids, which is really interesting. As well, we saw a direct relation between a higher CO2 consumption and a higher caproic acid yield, so concentration, sorry. So we can see that the CO2 is also key in the process of elongation. And we tested as well bioaugmentation strategies. As we know, Clostridium cluveri is key in the process. We cultivate it outside the reactor and we add it into the elongation. And we saw a slightly increase of the concentration of caproic acid. So considering all these results, and as we saw that, well, we achieved a conversion of a 30 more or less of CO2. It's not a lot, but it's a start and it's a good way to see other pathways to decarbonizing industry. So with these results, our another partner of the consortium, AINIA, designed the process for the upscale. They did the PNID, and they designed the upstream process and the downstream as well. They have purchased all the equipment, and it's pending the commissioning and the assembly of the pilot plant that will be soon in the Maus Lleida facilities, and we will validate all the things that we have done, all the experiments that we have carried out at laboratory scale in the industrial plant. And with that product, we can do other validation steps. So this is the main overview of the downstream process. I'm not an expert, but I know it finished with the downstream, the downstream finishes with the spray drying in order to obtain a dry product, a powder that we are able to use for feeding piglets in this case. So in the CIRCE proposal, the idea was to validate the ingredient in feeding industry, in this case with piglets. So for the validation trial, we are going to conduct several experiments with the CITA, which is a research center related with feeding industry. And they have chosen 40 piglets, and we have, in collaboration with them, chosen the best composition for testing how this caproic acid mixture or volatile fatty acids mixture improves the digestibility. So we gave them the main composition of the process, the ones that we have obtained best total volatile fatty acid composition, and the one that we obtained a better concentration of caproic acid. They selected the second one, and the idea is to acquire these volatile fatty acids, synthetic ones, in order to guarantee the food grade of the product and to make the test, the in vivo test, in a secure way without risking the piglets, of course. And then we could try and we could see if these ingredients are really beneficial for the feeding industry, as we think. So the main conclusions of the project is that this CIRCE project demonstrates that the biorefineries are key for transforming brewery byproducts into high-value products, and they contribute to a circular economy as well. The CO2, the decarbonization is key in this biorefineries process, and we need to decarbonize the industry. As well, we have evaluated that elongating volatile fatty acids is possible with CO2 as carbon source and ethanol as an electron donor, and we have done the optimization of the process by controlling the pH, the CO2 consumption, and the hydraulic retention time. As well, these results confirm that the key of everything is the substrate, because the bagasse or the spent grain, the quality that it has is key in all the process. And finally, just saying that it's another route, another way of biologically decarbonize the food industry, in this case, the brewery. Thank you very much for your attention.
Thank you, Carolina. That was very interesting, and I see there are questions in the chat.
Okay.
So let's go for them. Yeah. Bohan is asking regarding the functional organism for elongation. Is it a pure strain application or mixed culture? And what is the selection criteria of the strain?
It's mixed culture. I mentioned the Clostridium because it's the key one in the process, but we use the mixed culture that is already in the effluent of the acidogenesis. We just control the population by controlling the parameters in order to achieve better goals, but we don't use only one strain.
Okay. And Robin is asking, do you also include brewer spent yeast in the bagasse, or is this only brewer spent grains?
We have done the process with brewery spent grains because we evaluated the composition of the yeast as well, and it was better the spent grain for the process.
Okay. Yeah, I'm seeing, yes, there are more questions coming, great. Liliana is asking if this caproic acid-rich VFA mixture is intended for animal feed applications, what inclusion level would be considered safe and effective in pig diets?
Sorry, is intended for...
Yeah, how much can you include of your caproic acid mixture, VFA mixture?
I think it's a 10% of the diet. It's the volatile fatty acid, the medium chain fatty acid mixture is an ingredient of the final diet, not everything. So I think it's between a 5% a 10%. But there are several papers and articles that say that they give a lot of benefits for the digestibility. So it's interesting. Yes.
Yeah, I was going to ask that. So it improves the digestion of the animal.
Yes, and specifically caproic acid has antimicrobial properties, so it's good as well. Yes.
Okay. Yeah, we have so many things. Misa asking, since you use the mixed culture for VFA production, is it safe to introduce this VFA mixture in the food chain?
Yes, it's supposed it's safe because we start from byproducts, not from wastes. I think that's the key. If we with the biogas, it is possible. But however, as we don't know, we don't have guarantees. That's why we're going to acquire the volatile fatty acids for doing the tests. So we want to guarantee the security of the process. But yes, the culture, the population is not bad. The mixed culture that grows in the biogas is safe.
Okay. And Yasin has a question. Do you use any pre-treatment for the feedstock?
Yes, asking to the to the one before, I want to add that we do a downstream process. So we are not going to have microbials alive in the final product. And the one of the pretreatment, well, we mixed the biogas and the wastewater we wanted to have a really mixed substrate in order to feed the digester, but nothing else.
Okay. And I have a question also more on the digestion. So I understand some of the carbon gets converted into volatile fatty acids, but then do you still have a solid residue in this reactor? I assume yes. And what do you do with it? And can you use as animal feed? Because I know that the brewer's spent grain is actually usually used as animal feed. So how does the process?
But do you mean in the first process or in the second, in the acidogenesis or in the elongation?
Acidogenesis.
Okay. Yes, what we do is from the acidogenesis, the effluent is we put it all in the elongator reactor. So, you mean the solid part?
The solids, yeah.
Okay. No, with the solid, we didn't do anything yet. We will see. But I think maybe we can use the solid for producing char or something like that, biochar.
Okay, but you don't think it could feed back to the animal feed? Because that's the problem when using a waste that already has a little application. I know it's not the highest value application, but I guess the value chain is already there. So maybe something to consider, that if you could feed it back into the animal pathway, then okay, it's not a problem. You're just creating more value out of it. But
it could be.
Yeah, it's something that I'm thinking now as well. I'm going to start working with brewery spent grains, but in my process, I would just do a first extraction. Just take some like very available nutrients and sugars, and then the grain would still be there, so it wouldn't disrupt the value chain.
I know in the CIRCE project, they use all the biogas, for example, for the insect protein production. So maybe growing insect in that digestate, or effluent or solid part, is a good idea because they grow easier.
True, and then you have a more valuable protein source for the
or a solid fermentation could be as well.
No, okay, interesting. Yeah, I was just thinking because I'm starting also working with this type of waste. There is one more question. If you're not using pretreatment, how the microbes can withstand the side products? Is there any inhibition effect?
With this kind of substrate, we didn't have any inhibition effect. So as I mentioned, we had to progressively exchange the diet, the substrates in order to have the population we wanted. But there wasn't any inhibition. What we try to do is to improve the process by controlling the parameters. I don't know if I answered correctly.
For me, it's clear. We will see if Yasin, if you have any more questions, just put it in the chat. Okay, great. I don't see any more questions coming. My questions were also answered. We're a little bit ahead of schedule, but that's perfect because we still have 3 presentations after the break. So I would just call the break now. Okay, I'll give you a 10 minutes. Thank you so much, Carolina. Yeah, again, if anybody still has questions for the speakers, just put it in the chat and I invite the speakers to answer there. But then we can take a little break and we will be back at 2:55. So see you soon. Okay, welcome back, everyone. We're going to start now our second session. So we're going to go from the food industry to a more agricultural setting with CO2 recovery and valorization from biogas. So we will start with the Agri CO2 project represented by Sander Vandendriessche today.
Yes.
It's a big last name.
Yeah, and a complicated one for non-Dutch speakers, yes.
Yes.
Let me share my screen.
Yeah, I don't hear you now, Sander. I don't know if it's me.
Okay, and now?
Yes, now I hear
okay.
you.
Perfect. Yes, sorry. So good afternoon, and thank you for the opportunity to give a presentation during this webinar. In this presentation, I will talk about Agri CO2, which is a Flemish project in which we look at CO2 recovery from agricultural activities, like for instance biogas plants, but also how we can use this recovered CO2 again in greenhouses to really close the cycle at agricultural level, to say so. So first of all, why do you need CO2? As you all know, plants and crops need light energy, but also carbon dioxide for their growth. So it's very important that we add these to closed environments like in greenhouses. Just to stimulate the growth, it's a really important aspect that we add carbon dioxide as well. And yeah, you can see it clearly on this graph, especially in greenhouses. It's important to dose additional carbon dioxide as the production will increase with more CO2. In the outside air, there is on average about 400 ppm CO2 available, but crops will have a higher production when there is or when the CO2 concentration is higher. For instance, for growing tomatoes, the aim is 600 to even 1000 ppm CO2. And you can see this clearly on the graph. When there is about 1000 ppm CO2, there will be a production increase of about 30%. And this is also the case for other greenhouse crops. So it's not only for tomatoes, but for greenhouse crops in general that we need to add CO2 to increase the production. So since greenhouse crops need CO2 for the growth, we decided to initiate an operational group working on this topic. Not because it is unknown, because yeah, CO2 dosing is already standard practice and it is done in almost all greenhouses. But we wanted to initiate this operational group because it is more and more important to find alternatives for the fossil-based CO2. For instance, the Fit for 55 package states that that we need to reduce the fossil CO2 emissions by 31.3% by 2030, and also Scope 3 emissions are becoming more and more important. And therefore, the main goal of this operational group is to look into alternatives for the fossil-based carbon dioxide. So on this graph, you can see the emissions of CO2 equivalents in Flanders, and it can be noticed that agriculture, which is the orange part of the graph, is responsible for about 10% of the Flemish greenhouse gas emissions. So that's already quite significant, I would say. And if we look more in detail into the distribution of these emissions in agriculture, it can be noticed that heating greenhouses and buildings, which is the light blue part of the graph, is responsible for 26% of the total agricultural emissions. And there is a target to decrease the emissions towards 5.1 million tons CO2 equivalents. So if we can decrease the emissions coming from heating greenhouses, this will significantly contribute to the total decrease in emissions. So as a consequence, to decrease the emissions, the government wants to promote alternative heat sources and electrifications also in greenhouses. This means fewer CHP hours, which is quite common in greenhouses. So for now, what is often done is that there is a CHP, a combined heat and power unit in greenhouses that is burning natural gas to produce electricity, heat, and also carbon dioxide. But the consequence of having less CHP hours is also that we have less production of carbon dioxide available. So we need to look for alternatives that are also fossil-free. However, it's important to know that this fossil-free carbon dioxide should be free of toxic pollutants like NOx, SOx, and ethylene. So it's really important that we also take this into account when looking for the alternatives for fossil-free carbon dioxide. So in our operational group, AgriCO2, we will draw up a decision matrix of possible alternative CO2 sources for greenhouse horticulture. These alternatives could come from, for instance, waste incineration, industrial processes, but also composting facilities and biogas plants. And in the project, both growers as well as potential suppliers are involved in order to make sure that all different types of stakeholders of the whole value chain are able to give their inputs. So it's an operational group, so it's not fundamental research, but the aim is really to bring all types of stakeholders in contact with each other to increase the value chain. As this webinar is mainly focusing on CO2 recovery out of biogas, I will only focus on this potential pathway during the rest of my presentation. And on this figure, you can see what is usually being done with biogas. So I will not spend too much details on it or not spend too much time on it. But what is mostly done is that biogas is directly being burned in a CHP, producing renewable heat and electricity. However, if we look into upgrading it to biomethane, which is gaining more and more attention over the last years, the goal is to increase the methane content of the biogas. And there are several ways to produce biomethane. The two most common upgrading technologies are membrane separation and pressure swing adsorption. And by implementing these technologies, you will split the biogas and methane on the one hand, but also a quite pure CO2 stream on the other hand. And the main advantage of this biogenic CO2 is that it is carbon neutral. It is also continuous available because biogas is, of course, also a continuous ongoing process. And there is a growing market because the biomethane the biomethane production is growing over the last years. And last but not least, it's also a very good example of circular economy because we use the resources at its best. So the European Biogas Association published a study about biogenic CO2 from European biomethane, and it could be concluded that to date there are about 125 plants producing in total 1.17 million tons of carbon dioxide annually. However, there is potential to even increase this to 89 million tons by 2040. So there is a lot of potential to produce biogenic CO2. And if you look at the potential for Belgium, for instance, we see that by 2030, we can produce up to 400 million cubic meters of biogenic CO2, which corresponds to 790,000 tons of biogenic CO2. So also here in Belgium, there is a big potential to really use more biogenic CO2 from biogas plants to, for instance, use it in greenhouses. And if you now go back to the horticulture, there are three possibilities to replace the natural gas and the fossil-based carbon dioxide. The first one is to simply replace the natural gas by biogas. But here there might be a potential issue with contaminants. Also, the grower would need to build and manage a biogas plant on the farm, which might be challenging because there is no continuous feedstock available at greenhouses. So there should be a cooperation with a nearby biogas plant, I think. The second option is to buy biomethane via certificates. So in fact, nothing will change for the greenhouse, but it will not be seen as fossil-based anymore. But of course, this will come with an additional cost. And then the third option is also to completely get rid of the CHP, and biogenic CO2 can in this case be imported directly from a nearby biomethane plant. In this case, the grower would need to have alternative energy production, so he needs an alternative heat source and electricity source as well. This is not done in Belgium yet, but in the Netherlands there are already examples of companies doing this. For instance, the Sustainable Food Plant produces about 80 million cubic meters of biomethane each year and 20,000 tons of biogenic CO2. And this CO2 is then used in nearby greenhouses. And next to this, the digestate is also being converted into organic fertilizers. So this is a great example of circular economy. For my last slide, I also added the capture cost of biogenic CO2 as it is calculated by the Biomethane Industrial Partnership. I won't go too much in detail, but it is expected that by 2050, biogenic CO2 out of biomethane will cost about 25 to 90 euros per ton, which is cheaper than some other sources of carbon dioxide. And an extra advantage is that it is quite pure, because when we have the separation of biogas into biomethane and carbon dioxide, we see that the CO2 stream coming out of it, that it is a quite pure stream, and that it can be used directly in a greenhouse, for instance. Next to this, you also need to take into account the transport cost. So of course, the more nearby the biogas plant or biomethane plant, the better, of course. So this was in a nutshell, a very brief introduction about our operational group. As I mentioned, it's not about doing fundamental research, because we know these kind of things are already possible. We see the example from the Netherlands, for instance, but it's more about bringing several types of stakeholders in contact, and mainly to see if we also can do these kind of things in regions like Belgium. So if you have questions, I would be happy to answer them, or if I cannot answer them, to pass them to my colleague Martin, who is the coordinator of this project. Thank you.
Yeah, thank you, Sander. Very nice project. I personally like when these small projects that really are focused on implementing a technology. I think we have sometimes a bigger impact with the smaller projects. So very interesting. For now, I don't see any questions in the chat, so I'll start. But yeah, I invite the participants to put some questions if they have. I was just thinking more towards the last part that you were discussing, how to implement this. I was thinking, because indeed, normally the anaerobic digestion plants, they produce the biogas, and then they either will do the upgrading to biomethane that we will see in the next presentations, or they will just burn it in the CHP immediately in their facility. But I'm wondering if there's any development, and I don't know if you know, about just capturing this gas into gas tanks and really selling the biogas as natural gas, and then I don't know, the horticulture could just buy biogas and put it in their CHP.
I think from a practical point of view, it's definitely possible to just store biogas in bottles, to say so. But I think it's more easy to upgrade it to biomethane and then just use the natural gas grid to inject the biomethane on it, because the infrastructure is already there. Okay. And then we can use this for transporting the biomethane in that case. So I think it makes more sense from a logical point of view to first go to the biomethane, then use the natural gas grid to transport it to where we need it, instead of transport or filling bottles with biogas, to say so, and then transporting this.
Okay, but so then a possible larger picture solution would be that the country does a transition from the natural gas to biogas and biomethane in their gas pipelines, and then the operator of the horticulture can just use the gas from the pipeline, because that one would be green.
Yeah, well, that was one of the possibilities I mentioned. It's this slide. So then, in fact, here on this slide, I mentioned that when a biogas or biomethane plant is injecting biomethane on the natural gas grid, then a greenhouse horticulture or a grower, he can just buy certificates, but still use the natural gas. Yeah. But he buys he pays for the green biomethane, and then it's via certificates.
Yeah. No. Okay. Very interesting. Yeah, it's nice we have the CO2, but indeed the logistics sometimes of getting the CO2 where it needs to be, it's a very interesting point. Yeah, I see there's not a question in the chat, but there is a comment. So maybe you would want to see. David is saying that there are some UK estimates in a report that might be relevant for you.
Yeah, that's very interesting. I will have a look. Thank you.
Yeah. Okay. If there are no more questions for Sander, I don't see anything coming, then I thank you very much. There's a side question. That's see, now I'm curious. Yes, Thibault, I think he's writing. And if it doesn't come, I'll just move forward and then you can answer in the chat.
Yes.
Yes, here. So you mentioned the CO2 that is fossil free should not contain NOx and the SOx and all that.
Yeah.
And why is that?
Well, I'm not a specialist for horticulture, so I'm maybe not the best person to answer this question, but I do know that at least ethylene is a big problem in greenhouses, so we should prevent it. I don't know about NOx and SOx, to be honest, but I can ask my colleague Martin, who is a specialist in greenhouse crops, to answer this one, but I think it's indeed about preventing that the plants take it up, I think. But I should check it with my colleague to be sure.
Okay, thank you. Then, I thank you, Sander. Very, very interesting. Good luck with the further implementation of the operational group. And I'll call our next speaker. Our next presentation is actually a double feature, so we will have two speakers. We will start with Stefano Rebecchi, and then we'll go to Petro Samaras, and they're both also representing the FUELPHORIA project.
Yes. So, hello, everybody. Yes, as indeed, as Marcella said, this presentation is actually divided into two different presentations. So I will start from the production of liquid biofuels via a two-stage fermentation process from biogas. So indeed, this is one of the demos of the FUELPHORIA project. I would like to start with an introduction of FUELPHORIA project because we already discussed about it, introduced it, but not but an overview has not given yet. So the FUELPHORIA project is a 4-year EU-funded project with a budget of approximately 11 million euros. Coordinator of the project is CERT from Greece. There are 22 beneficiaries in this project, and here you can see a map of the location of each of the partners. So the objectives of the demos this project are mainly the demonstration of a robust and cost-effective technological solution for the production of advanced biofuels and RF&BOs, build a portfolio of sustainable, secure, and complete value chains for advanced biofuels and RF&BOs from feedstock, and promote the exploitation of advanced biofuels and RF&BOs. So, as I said, one of the aims is indeed to demonstrate the production of these biofuels from feedstocks. So, as you can see from this slide, the project is divided into demos. So, indeed, the final aim is to demonstrate at, let's say, a pilot scale each of these demos. The first one is located in Belgium. I will talk about this demo later. The second one is located in Spain, and Sergio introduced and showed the results of this demo during the first presentation. The third one is located in Greece, and it will be presented by Petros after my presentation. And then we have the fourth one located again in Spain. So I will start, I will present indeed demo one, which is, as I said, located in Belgium. This is the general scheme of the demo. So we have indeed the first step is indeed the production of a biogas, which is sent to a biogas upgrading where it is CO2 and biomethane are separated. Then the CO2 is sent to a first gas fermentation process, and it is actually a gas fermentation process where the CO2, the biogenic CO2 from the biogas plant is converted into acetic acid, acetate. Then the acetate is sent to a second fermentation, a liquid fermentation, where yeast or bacteria convert acetate into TAGs, so microbial oil. Then the last step is actually a thermo-catalytic process, where the microbial oils are converted into biofuels. I would say that the main, let's say, technology involved in this project is the two-step fermentation process. So first, a gas fermentation of a biogenic CO2 to acetate, and then a fermentation, let's say traditional fermentation to produce microbial oils. So the project was actually divided into two main steps. So the first one was indeed the optimization of some of the steps involved in the demo, and then the upscale of the process. So in this slide, I will show the main results from the optimization at the laboratory scale. So here at the BioBase, we were able to optimize the gas fermentation process, and we developed a robust continuous fermentation process. We were able to run a gas fermentation in continuous mode for more than 60 days. And we reached the consumption rate of CO2 above 70%. So actually, this process is actually really robust and, let's say, already ready to be scaled up. Our partner, CSIC, developed some oleaginous strains for the production of TAGs. Particularly, they produced three different strains of Arroyo Politica, and also developed a bacteria strain. And then at BioBase, we optimized the liquid fermentation step. And actually, we already worked at, we tested the process at different scale, 4 liter and 30 liter scale, optimizing the process and also increasing the productivity and concentration of oils. And also super important, because obviously after a fermentation, we have a fermentation broth. So we had also to optimize the recovery of the oil for the next step. So for the production of a biodiesel, of a biofuels. And we were able to optimize the protocol and reaching a 70% of recovery yield of the oils from the cells. Our Greek partner and also the Greek partner, they tested initially, let's say, characterized the oil produced during the liquid fermentation. And they also did an initial biodiesel synthesis test. And actually the iodine value, which is actually a value which indicates the quality of a biodiesel, says that it is actually not the best, this kind of oil, but yeah, as I said, this is only the initial experiments. So we really think that we can produce a nice oil. Let's move to the upscale, probably maybe the most interesting part of a process of a project. So as I said, we optimized the process at the laboratory scale, and then here then we had to do also the scale up. So one of the challenges that we faced was to integrate the gas fermentation unit with the biogas plant and the upgrading plant. The biogas plant was located in Antwerp, at the wastewater treatment plant of Aquafin, and we had to move and integrate, let's say, the mobile gas fermentation unit from BioBase pilot plant to the upgrading plant. A few months ago, we were able to do the integrate them. As you can see in this picture, you have the biogas plant, then the upgrading plant, and the mobile gas fermentation unit. We integrated them and we started doing some tests. A couple of weeks ago, we concluded our experimental scale-up test at the site of Aquafin. And I cannot show in this moment any results, but I have to say that they are really promising. So we were able to use the biogenic CO2 from the biogas upgrading plant and convert it into acetate. In this moment, we are writing a paper, so extremely promising. Next step in the project is actually the scale up of the liquid fermentation. So produce at a bigger scale. We will try to we will produce at a bigger scale. Bigger scale, it means at 15 cube TAGs. And we will also develop and scale up indeed the recovery of the TAGs. The aim here is to produce hundreds of kilograms of microbial oils. And then those oils will be sent to the partners for the thermocatalytic production of the biofuels. So really just concluding and summarizing the main results, we were able to optimize the gas fermentation process. We reached a consumption of CO2 above 70%. We enhanced the productivity and concentration of the liquid TAG fermentation, and we were able to increase the productivity, the recovery and purification of the TAGs above 70%. We also did we were able also to scale up the gas fermentation using indeed the biogenic CO2. This task is concluded, and the next task include indeed the scale up of the fermentation for the production of a microbial oil and the upgrading of a microbial oil for the production of a biofuels. So this is all for my presentation. If you have questions, I'm here.
Okay, thank you, Stefano. Yeah, I'll see if there are questions in the chat. For the moment, no. So maybe I'll ask a first question and then we see, and then we can move to Petros and maybe we come back and then continue with the little questions. But yeah, I was just wondering, again, a similar question that I asked for your partner in FUELPHORIA in the first one. How is the energy balance of this process? Because I assume, but maybe I'm wrong because I don't know, I never worked with gas fermentation, that you need to pressurize maybe your reactor to get these high CO2 conversions, and maybe, I don't know how the energy usage is, and at the end you want to produce biofuel. So yeah, did you do any energy balance? Do you know how this is looking like?
So it is ongoing, the energy balance. But I can give you some, some, let's say, ideas or things that we already know, because the pressure is one thing, but actually we really don't work at really high pressure. Okay. I would say that probably in this moment, one of the main costs is the production of hydrogen. Because it's needed. We need hydrogen. We need the energy source for the microorganism. And in this moment, I think that it is the main, let's say, obstacle for. So yeah. Okay, interesting. Well, good that there's a lot of research on hydrogen generation as well. So hopefully they will have a breakthrough that helps your technology. But okay, I would then move to Petros, and then we can do a combined question and answer session.
Okay, thank you. Good afternoon. I'm trying to share my presentation now. Can you hear me?
Yeah, I hear you.
Okay, good. Let me see. Here we are. I guess that now you can see my presentation. So
yes,
that's the other demo of FUELPHORIA project, and thank you very much, Marcello, that you invited us to present our efforts here, our work in the project. I'm happy that Stefano has already presented the different demos from FUELPHORIA. This is demo 3 that takes place in Greece with the involvement of several partners around Europe. What we are going to see here is this, as you can see from the title, that from biogas plants to liquid biofuels via microalgae. I'm Petro Samaras. I'm professor at the National Hellenic University. We are located in Thessaloniki, northern Greece. And the main task here is the examination of long-term production of biodiesel from microalgae. We are going to see what is the problem then in the next slides, but in general, digestate is produced from biogas plants with sometimes a very high nitrogen content. Sometimes it can reach up to 5 grams per liter. And in that case, we need an alternative process, an alternative method to handle it, since disposal or discharge is not allowed. And in that case, we can use some natural species, microalgae, for cultivating in this digestate. We can use digestate as a feedstock, as raw material for nutrients supplement to microalgae. And of course, then we have to consider how microalgae can be used, since, well, we can have large amounts of biomass. But since we know that microalgae can contain different components like proteins or lipids, then we should consider how we can valorize this microalgae. And this is the main concept, to use these lipids for production of biodiesel, something that someone could say, well, there are hundreds or millions, I don't know, reports in the literature of how to produce biodiesel or lipids from microalgae, or how to turn lipids to biodiesel. But if you go in details on in all these reports, you can see that almost all these studies are taking place at lab scale. And there isn't any space to consider what is really the cost, the feasibility of this process, and if this biodiesel that is produced can have a comparable price like the market biodiesel, the conventional, which is produced by conventional methods. And this was our target, to have a demo, a large-scale application, and to see finally what is the feasibility of the process. If we are able to produce this biodiesel from the residues or remainings of a biogas plant. This was the main task. This went through or goes through different tasks, starting from lab scale test up to large scale demo units, and it considers all the entire process from microalgae cultivation up to biodiesel production. And there are several challenges and several issues that we have to deal with in that case. And the main target here is the production of biodiesel. Of course, this is the end product with the participation of several partners. You can see here Algen, IHU, this is International Hellenic University. Algen is a partner from Slovenia. QLab and Vert are Greek partners dealing with either the analysis or the production of biodiesel from lipids. And the final targets in our works is that we need biodiesel to be used in different applications, like as a fuel for road transport, or as a fuel that can be used for power production in isolated areas. And this goes through a process that includes different units, different processes. We start from the biogas plant. This is a plant which is located in Greece. Let me see, there's a delay in my presentation. Okay, sorry. Okay, here we are. And the biogas plant that we are using now is a plant working with livestock production. And in that case, we can see that the operators, or we have to see that the operators are trying to find very cheap raw materials, very cheap feedstock, in order, to reduce the overall cost of their plant. And in their effort to find these raw materials with low price, they can use different feedstock, different materials like chicken manure. And because of the chicken diet, this manure can have high nitrogen content, which is finally found at the digestate, the effluent from the digester. And in that case, we can have contents as high as 5 or 6 grams per liter, as I said before. And on the other hand, we have the production of carbon dioxide gases in the flue gas from the biogas generator or in the biogas itself. So digestate is used then for microalgae cultivation. Of course, for the large-scale cultivation of microalgae, we need to start from a smaller inoculum, so from a smaller culture, and we use the same digestate for the cultivation of this inoculum, which is then transferred to large-scale ponds. You can see here that there are 2 ponds, and the system takes place in these 2 different units, and this is because we need to have a tailored composition, a desired composition of the cells with high lipids content. And in that case, the first pond is used for growth of biomass, while the second pond is used for starvation of microalgae under a low nitrogen diet in order to turn their composition to high lipids content. And we have these demo units, which are which include the 500 square meters ponds, each one, and then biomass from the algae pond are going to harvesting, collection of biomass and concentration of biomass through settling tanks, and the concentrated biomass is used for lipids extraction. We can see here that there are several issues that have to be addressed about how we can make this extraction. Lipids that will be received, that are received from the extraction, then are subjected to some kind of fractionation in order to be purified and used only the desired fraction for biodiesel production again. The system went through 2 different work packages. The first one was the preparation. We had to start first for the determination of the digestate properties variation, since, as I told earlier, the unit uses different feedstock. And in that case, the digestate also has great variation in its composition, and you see that ammonium content can change from 1.5 up to 5 grams per liter, and also phosphorus can vary from 40 milligrams per liter up to 1.2 grams per liter. And these are the basic nutrients which are required by microalgae. And as you can understand, when there is such a great influence of feedstock, then we cannot ensure that we are going to have a standard growth of microalgae or even standard composition. And then we have to find also which are the best species, because there are different 100 species that can be grown in digestate. We used different species, but what we would like here was not only to find species that can survive in digestate, but can have also high growth rate, and in addition to give cells with high lipids content. Of course, the design of our system, you can see here the drawings that we used for the 2 ponds and the smaller pond, which is used for inoculum preparation. And then we had also to install a greenhouse above the ponds, and this is because we didn't like to have any kind of other impacts from environmental factors or even contamination, which is something that we are going to discuss later. And this is a photo of the system while it was in construction, the demo unit. You can see the greenhouse above the pond, and you can see one of the pond of the 500 square meter pond. the preparation and the modification of the biodiesel production unit, a 250-liter unit which is located in Volos in central Greece, and they are going to receive the lipids from our extraction to turn it to biodiesel. And something which is also quite interesting, to prepare a model software that would allow us to have a prediction of the system response at the different conditions. And then we have the large-scale implementation of the project, where we started from the different species cultivation in order to check if the lab-scale experiments are valid and are also correct for the large-scale application. Different species that were tried. Of course, we are going to use a cocktail, a mixture of these species for the demo system. Demo system in operation. It has been started around 2 months ago, and now we are working for production of biomass. Biomass produced from a pod will be separated from the liquid, the aqueous phase, in a settling tank, and then this concentrated sample will be used, or is used right now, for extraction of lipids. And let's see what's the problem here. Usually the solvent which is used is hexane. And I'm trying to catch the question from Marcella about the energy optimization. If we would use hexane, we had to make the mixing of hexane with algae, and then we had to separate the hexane from lipids in order to get the pure fraction of lipids. But hexane can be removed from the system by distillation, which means